co-founded Tartarus Data. In 2018, he co-founded Sabut Foundation in Mohali, Punjab, to train engineering students in machine learning and to work on social problems in education, farming, governance, and healthcare. And at present, Dr. Anand is working as adjunct faculty in Indian Institute of Science, Education and Research, Mohali, and director CSC at Munjal University. We welcome you, sir. And we are really lucky to have you here on this session here. And I hope our participants and students will get maximum out of you. Whatever you will be delivering today, I think you are delivering on recommender system, right? Okay, sir.
That's correct. That's correct. Thank you, Dr. Kiran Jyoti, for your very kind words. It is actually indeed my pleasure always to be invited to Guru Nanak Dev Engineering College. I'm really excited about the talk today. And my association with your institute has been longer than any other institute. So I'm really glad to be part of this.
So you are really kind.
Today.
Whenever we call you, you're always there. Thank you very much.
Thank you. So I can share my screen, I believe now. Oh yes, okay, perfect. So I shall start my talk today. As Dr. Kiran Jyoti said, I want to talk about recommender systems. This is an area that I did active research in while I was an academic, and was lucky enough to get into this field when it was a baby, right? So this is a field that was just starting, and in the 1990s, late 1990s, and I was lucky to get associated with it then. So as Dr. Kiran Jyoti said, I have my own company based out of Delhi and Mohali called Tartarus, where we provide AI and machine learning services to our clients who are mostly in the US, Canada, UK, but also a few clients in India. And along with that, I also was lucky enough to be able to found Sabut Foundation. In fact, along with one of your colleagues, ma'am, and 2.5 years ago. Sujit Sera sir, who is now in Canada, is an important part of Sabut Foundation. And without him, I don't think we could have grown Sabut Foundation the way we've been able to. I am also now associated with AIMLDS University, where I'm the director of computer science. So when we think of recommender systems, we probably all have used recommender systems for quite a few years now. When we go onto Amazon to buy products, we see other products being recommended to us as we search through Amazon. We also see on Netflix, which has of course now become very popular in India as well, the fact that we are getting recommended movies and TV series on Netflix. And of course, there are many other examples. Most e-commerce websites, most news websites are all using recommender technology. And so I thought today maybe we can go into understanding the technology itself behind all of these recommender systems. And really, recommender systems became a topic of interest because today we live in times where we have too many items and too little time to consume them, as long as, of course, we can afford these items, right? So the choice has become very large. While Google at that time had established itself as a search engine and was being used on the World Wide Web, the question that researchers started asking themselves was, why should we search when we can filter, right? And the idea of filtering is a little different from what would be search engines. So typically when we talk about search engines, we talk about an area of computer science called information retrieval, where the user would provide some kind of a query. And based on that query, our search engine will search this big repository of content and will return to this user then a set of results that match that query, right? And, so the difference between information retrieval and information filtering, of which, of course, recommender systems is a part, is the fact that with information filtering, what we hope is that we can actually provide the user with what they should be interested in without them asking an explicit query, right? So right now, if we go onto Google and we put in a query, of course, that's when we'll get results. If we just go there and don't put a query, we don't get any results, right? That's kind of surprising to me, given the fact that Google knows so much more about us than we know even about ourselves, right? So Google is tracking everything that we are doing, whether it's with our Android phone, whether it is on our browser. And so they have lots of information about us. And the fact that they don't actually attempt to predict, right, as to what we would be interested in is somewhat surprising to me, right? And so the idea here is that a user comes along, there is a very large set of items that need to be consumed or are available for consumption. And from this sea of items that we have here, we are consuming items through a very small interface, right? We've gone from, most of us are now on mobile phones, and the mobile phone screen is much smaller than the web. So while the web gave us lots of opportunities to expose a lot of information to the user, the mobile phone actually has a very limited interface. And so with this interface, which is our real estate on which we can actually present content, what we want to do is optimize how we use this content by providing what is of interest to this user without them having to ask for it. And this, of course, has had some bad press as well, because one of the ideas, and of course it's true to some extent, one of the ideas of information filtering is that it would put us into what is called a filter bubble, right? So the user now only sees what the AI algorithm decides is going to be interesting to them. And the truth of the matter is that that's happening to quite an extent, right? So, in the future, I can see that, Amazon will be making decisions for what we wear or what we, books we read. Because what we are typically looking at is the recommendations that we're getting from them, right? And so, compared to our browsing experience within a physical space where we can go and look at all the clothes that are on display within a shop, we are actually at risk in Amazon of only seeing what Amazon decides we should be shown. And that's the fear, right? So there's a lot of fear around artificial intelligence. This is the fear associated with recommender systems, that if recommender systems are given control of what we consume, then we will not know what is out there, right? And in fact, if you look at what's happening in America right now with the elections also, you can very clearly see that people are who are Democrat are only reading what Democrats want to believe in. People who are, on the Republican side are only reading what Republicans want to read. And there is a huge polarization that's taking place. And partly responsible for that is recommender systems. So today we're going to look at how do these recommender systems work and some of the algorithms behind it. So typically, we have two types of recommender systems: content-based filtering and collaborative filtering. So consider a scenario where you go to the Times of India website or the Tribune website, and today we have the technology that when I go onto the Tribune website and one of you goes onto the Tribune website, we could have a completely different experience, right? Where stories that I have consumed in the past could be used to create a profile of me and my interests. And so we have the ability to create a completely personalized interaction compared to what we had when newspapers were consumed because they were dropped into our houses, right? Where we had the same newspaper, obviously because it was printed, going to all of us. And I may have spent more time on the sports pages. Somebody else may have spent time on local news, and a third person may have spent time on the page where you had international news. And so content-based filters are simple filters that say, let's look at, out of all the items that could be consumed, in our case, we are talking about news stories, right? So these could be news articles. And in the past, this user may have consumed some of these news articles. So from these news articles that have been consumed by the user, we create a user profile. And we call this user the active user, right? So this is the person that we now need to recommend news stories to. So content-based filters take all of the stories that have been consumed and create a profile for this user. And I'm sure during the course of these 5 days, you have been taught about text analysis. And a very important part of text analysis is this idea of vectorization of code, right? We will look at it if we have the time today. But essentially, vectorization of code is where we convert a text document, in our case, a news article, and represent it in some high dimensional space, right? So we would actually have maybe a space that goes from 1 to the number of unique words in the language that has been used to write these news articles. And once we have this representation, then a content-based filtering approach would essentially look at what's a good match of the stories that have not been consumed by this user to stories that he has consumed in the past, and we would then recommend stories back to him. So say, for example, I go into a news website and I read stories about cricket. The problem with content-based filtering is that because my user profile will be about cricket, I will only start getting cricket articles, right? And this is what we were referring to as the information bubble or the filter bubble, right? So the problem with content-based filtering is that typically they have a narrow vision and there is very low diversity in what gets recommended to the user, because you're just matching what has been consumed by the user in the past, in my case, cricket, and serving up articles that are similar in nature. Now, back in 1994, in the University of Minnesota, there was a professor called John Riddle. And John Riddle, unfortunately, he passed away a few years ago. But his group there came up with an algorithm which was referred to as a collaborative filtering algorithm. And what the collaborative filtering algorithm tried to do was to say, well, can we get away from this low diversity that we get in content-based filtering? And the other question they asked themselves was, what if items do not have descriptions associated with them? Now, in news articles, of course, it's content that's being consumed, so there is item descriptions. But what about movies, for example, right? Can we actually recommend movies without having a description about the movie? Of course, typically in movie websites also, we have the plot, we have the title, we have the actors, we have directors, and we can use all of this information, production houses, right? We can use all this information for recommending similar movies. But what if we did not have access to good data like this? And so they built these algorithms called collaborative filtering that utilize not only the current user that for whom we have to make recommendations, but they also use the wisdom of the crowd, right? So essentially all users that have consumed any content are part of the knowledge base that the collaborative filtering algorithm uses. And the idea here is that rather than using a content-based description, we will create, and we will go into detail on this, but we will create what is called an item rating matrix, or a user item rating matrix. And what you have here is a matrix where every row is a user and every column is an item, right? The items could be news stories, they could be movies, they could be products being sold by a website, whatever. And in here, we have a rating given by the user. So say this is user U2. The rating given by U2 to item IK will be stored in this cell here, right? And we call that R2K. Similarly, we would have a row for our active user here also, UA, and he will have, or she will have, rated different items. So we consider the row here to be the user profile. And because the row has a set of ratings in this M-dimensional space, we can think of every user now as being a point in an M-dimensional space. So I can only show 3 dimensions here, but essentially what you have is a very high dimensional space, very high because most e-commerce websites, let's look at Netflix, for example, probably has, 50,000 movies, right? So we are in a 50,000 dimensional space here where a user can be represented as a dot, right? A point, which is determined by the ratings given by the user to each of the movies. So now you have active user UA, and you have other users that are also present in this space, right? And so what you do is you define what is called the neighborhood of A, which is the closest users to UA, right? So once you have this neighborhood of users, we basically look at all of the users. So, right, so this might be a user that's similar to UA. This might be another user that is similar to UA, and this one again, right? So say we had these 3 users. Now what do? We look at, clearly if these users are in the neighborhood of user A, then these users are going to have rated in a similar fashion some of the items that user UA has also rated. But those items that have been rated highly by these neighboring users that have not been consumed by user UA then become recommendations, right? So an important part of collaborative filtering is storing user item consumption for all users and then using it together to make recommendations to the user UA. Now, collaborative filtering has the advantage that, as you can see, we are not using any item descriptions. So there's no need for item descriptions here. If they are available, we can't even use them within collaborative filtering. So that's one aspect. The other aspect of this is that, say I have read cricket stories only, all of my neighborhood will have read cricket stories, but then if one of these people or 2 of these people had read about politics, I would start to get recommendations of politics news stories. So I have greater serendipity, unexpected recommendations, right? And the big advantage here is really around the fact that we have these unexpected recommendations. So we have no more got the problem of low diversity. Now, at the same time, collaborative filtering has certain downsides to it. And one of the problems with this algorithm is that if you have a new user, a user that has not consumed anything up until now, because the profile of the user depends on what they have consumed in the past to kind of find the neighborhood or define the neighborhood that they are in, we cannot make recommendations of any items to a new user because we cannot calculate their neighborhood. The other problem that this also has, so this is a negative, right, of collaborative filtering. Another negative of collaborative filtering is the new item problem. Remember what I said again here? What I said was that the items that get recommended to this active user are items that have been consumed by similar users to this particular user, right? And so if a new item is introduced that has not been consumed by a number of people in our customer base, then it cannot be recommended to a new user. And this is a bigger problem for retailers, right? Because what do they thrive on? Retailers thrive on introducing new items, and those new items being explored and consumed by existing users, right? Because keeping existing users happy is a very important aspect of e-commerce. So if you keep your users happy, they're going to come back and do more and more purchases with you and increase their profitability over time. And so these two problems are severe problems with collaborative filtering. And so what researchers then developed were these hybrid approaches that combine collaborative filtering and content-based filtering to address the shortcomings of the individual algorithms. They basically use content-based filtering to recommend new items and items to new users, and use collaborative filtering to get more diversity within their recommender systems. So let's look at a little bit of mathematical notation. So essentially, let's first look at what is the kind of data that's used in collaborative filtering. We're going to look at collaborative filtering first. So the first thing that we have in machine learning always is the data, right? We need data to do any machine learning. And so this should not come as any surprise that the starting point for machine learning must be data. What does that data look like? Essentially, it looks like these triples. We have a set of users, U, a set of items, I, and a set of ratings associated with items and users. So the triple here says user UJ, that's one of the users in our user database, along with an item IK, which has been consumed, right, by this user and comes from the item database, has been given a rating RJK, right? But the rating given by the jth user to the kth item. And that rating lies in a discrete set of values. And typically, as you know, the rating scale goes 1 star, 2 star, 3 star, 4 star, and 5 star, right? So typically R is 5, though of course some websites use a scale of 7 or 10 also. Now, as you have probably learned during these 4 days that have gone by, the whole idea of machine learning is to find an approximation of a function, right? So what we are saying here is there is this real world process. And the real world process in our case is consumption of items, right? And when users consume items, they rate those items. And that rating that they are giving is a measurement of their satisfaction, right? So we are interested, there is some function that lies within the real world that has generated this data. This data is a sample of all data that possibly can be generated by this real world process. We do not understand this real world process because this is a human process. And of course, humans are fairly irrational and are complex systems. And so we don't know what this function was, but there is some function that takes a user and takes an item and maps it onto some rating, right? So what we are trying to do is we are trying to approximate this function by learning from data. So this function f, which takes a user and item pair and outputs a rating in the scale of 1 to r, is trying to approximate this by using the data that is given to it for learning. And that's what all machine learning does, right? So what do we mean by approximation of a function? Well, we typically start with a hypothesis space, which is a family of functions. And what do those family of functions do? They essentially define a set of functions, one function differing from the other based on parameter values chosen. Right? So you have learned, I'm sure, about linear regression or logistic regression or ridge regression. With linear regression, what we are saying is that y is equal to beta 0 plus sigma beta I xi, right? And what we are saying is that the family of functions is the family of linear functions defined on the space that we have been given as our data model, right? So the xi's and y's are defined, and we are learning these linear functions that relate y with x. And each one of those linear functions are different from the other linear functions because of their choice of beta i's. So actually, when we look at this function here as well, it actually is a regression problem, right? Where we are saying that even though we have been given these integer ratings, we are actually trying to predict a continuous range of values, right? And to predict that, we are taking as input the user characteristics and item characteristics. Okay, so actually one way of thinking about recommender systems is to think of it as a rating prediction problem, and that's a regression problem. And whenever we have a regression problem, to tune our parameters, we always, of course, need a cost function. And the cost function that is typically used in regression problems is the mean squared error, right? And so what we are saying is that for all the user and item pairs that we have ratings for, we want our predicted value of the rating to be close to the observed value. Right? And this is the predicted value. And so we are taking the mean squared error, we're calculating the sum of squared difference between the observed and the predicted, and we are dividing that by the number of predictions that we have here, right? So what we are saying in this equation here, n is the number of triples in our data set. Right? I'm referring to it as the test data set here, because just like you know in any machine learning problem, given some data, you will split it into a train and a test data set, where the objective of the training data is to learn your approximation. of this function here. And then the test data, the objective of the test data is to be able to estimate the error. Right? And so what we are doing here is we are learning the mean squared error, which is essentially, measuring how off the observed ratings are being. So a question here is, sir, can other cost functions be used in it other than mean squared error? Of course it can be used. So that's a very good question. Thank you for asking that question. Of course, we can use different cost functions. Typically in regression, though, mean squared error is a pretty good option. Some people prefer to use mean absolute error, but essentially when we are choosing our cost function, what we want to do is we want to choose a convex cost function, right? And a convex cost function is one that looks like this, right? So it has only one minimum. And of course, in most cases, we can't guarantee that the cost function will be convex. And so we have the biggest fear of a machine learning engineer is, have I stopped in some local minima like here, right? Now, for a linear function, if we are using mean squared error, it is a convex function, right, that we are optimizing. And that's why with linear regression, we make this very simplifying assumption of linearity because we are guaranteed to reach an optimal solution. Now, of course, the downside of that, as you, I'm sure, already know, is that we can severely underfit the data. Why would we underfit the data? Because we made an assumption of linearity here. And if we have made an assumption of linearity, but this function that we are trying to approximate is not linear, then we, no matter how good our parameters are that we have chosen, we would underfit and not be able to approximate this function very well, right? And so the whole idea is to balance in machine learning, to balance the complexity of the function you're trying to fit with the risk that we then have of overfitting, right? And ending up in a local minima being the other kind of concern that we would have. Okay, so let's look in further detail on the user item rating matrix, right? So I've already said that the data looks like this matrix. We've got users down here and items up here. And of course, we have a user that is consuming movies, that likes movies because of these preferences. But he is not telling us those preferences, right? All he is telling us is, these are my ratings. And based on that, we are trying to learn this function. So this is the basic idea behind collaborative filtering. So here, for example, just to go a little deeper into the basic user-based collaborative filtering, what we are seeing here is that we have a small number of users here, and we are interested in Chan, who is our active user. Now, Chan has, we are assuming a rating that is, allows half ratings as well here. So Chan has liked Batman and he's also liked Superman. And so to come up with, will Chan like Inception? Right? That's one possible movie that we can recommend. The other movies that we can recommend here are these ones here. So what will we do here? We will essentially look for those users that have actually given good ratings to Batman and Superman and has given a poor rating to Spider-Man. So we will look out here and say, well, Leo seems to have similar tastes. We could possibly say that, this person Suresh here also has similar tastes and so on. And then based on the users that we have chosen here that become our neighborhood of UA, we will now predict this by looking at what were the ratings given in the neighborhood to the movie Inception, right? So one thing to recognize here is that we have a sparse matrix, right? And this causes some problems, and we will look during this lecture at ways in which these problems can be resolved. But essentially, we have a lot of missing data, right? Movies that people have not rated. And the other aspect of the sparseness is the fact that you can see here that in this very simple example, very often we are calculating similarity on less than even 3 movies, right? So here we are looking at these 3 movies, and fortunately we have an overlap in all 3. But if we look at this here, this person, Michelle has not seen Batman. And so we are basing our similarity on 2 of these movies. And Michelle becomes important for us to predict the rating of Inception because she is one of the few people that has seen the movie Inception, right? So there are all these different concerns that will come up in collaborative filtering for us to deal with. Now, think about the fact that we can add some more complexity here. So now this user may have these preferences whenever he's watching a movie on his own. Now add some context to this user. Now this user is watching the movies with his or her children, and suddenly the preferences change. They go to animation, Disney and Pixar, rather than being about cinematography and special effects and maybe dharma, right? And so the question is, hidden somewhere within these ratings are the preferences of users, and how can we learn user preference from this is an important question. And we will look at that. So the basic user-based collaborative filtering, what it does is what I've been describing up until now. We take this active user UA, we scan through all the users here and look for those users that are similar to user UA. We call that the neighborhood of UA. So clearly, if we are talking about similar users, we need to define similarity. And as I mentioned earlier, every user is considered to be a point in a high dimensional space. So this could be user A, this could be user K. And any point in a coordinate space can be thought of as a vector. And when you have 2 vectors, of course, vectors, as you know, have a magnitude and they have a direction. So they also, a pair of vectors has an angle between them. And if we think about 2 vectors, and for now, let's assume that the magnitude of the vectors is the same. So the magnitude is the length of the vector. Then when theta becomes 0, we would have one vector sitting straight on top of another vector. So they would be exact replicas of themselves. And in a space where all of our coordinates are positive values, right? Ratings are only going to be positive. We're not allowing any negative ratings. The maximum distance between 2 vectors would be if they have a 90-degree angle. So one is here and the other is here. So when theta is equal to 90, we want them to be most dissimilar. And then when theta is 0, we want them to be similar. And of course, the function that satisfies that is the cos function, right? So cos of 0 is 1. cos of theta, cos of 90 is 0. And of course, we know, that the cos of the angle between two vectors is the dot product of the normalized vectors. And what do we mean by the normalized vectors? We are saying a vector of unit length. So what we are doing here is we are saying VA and VB are our two users. We are dividing each of our users by the length of their vector. What is the length of the vector? It's equal to VA dot VA, right? So we are essentially taking that and square root of it. So we are dividing by the length. So now the lengths are the same. So the magnitude is equal. And the dot product of these two is cos of theta. I'm not going to go into the proof of this. You can, we can talk about the proof on the side, but essentially this is a well-known result in vector algebra. And we refer to this as cosine similarity. So now we have a similarity function. Given a target user, we can use cosine similarity to identify the closest users, right? So here we again have a simple example where we have 6 items and 5 users. We are interested in U4, who's our active user. And for now, let's assume that U1, U2, U3, and U5 are the neighborhood of active user A. And now we want to come up with recommendations. So we want to predict these ratings here. And what do? First of all, we calculate the similarity, right? And what we are finding here is the similarity with U4 is maximum for user U3. This is using cosine similarity. And the second closest one is U2, and then U1 and U5. So now that we have these similarities, and what I'm showing here is just the length of the vector. We don't need that for now. So what we are doing here is to calculate the predicted rating for this. We are essentially taking the ratings of all the users who have rated item I4, multiplying it by their similarity and dividing them by the sum of similarities. So we are taking basically a weighted sum of ratings. And this becomes our prediction algorithm. So here in I4, we've got 3 given by a user that is 0.517 similarity. Out here, sorry, this one here. We have a rating of 4 given by a user with similarity 0.735. Just a mistake here. And then we have a rating of 2 given by somebody who's not very close to our active user, right? And what we're doing here is taking the sum of each of these similarities. And this is just a normalization that's happening to ensure that the predicted value is again in the range of 1 to 5. So having predicted the ratings for each of these 3 movies now, we would recommend movie 4 to these users, right? Now, notice one thing here. So we are saying that user U3 is the closest to U4, right? And we can see that, yes, it is, right? I mean, it's given a 4 here to item 5, which was given a 4 here. And this user has given a rating of 3, which is close enough to 4, right? Now, what is kind of surprising though, is if we look at it in a different way. We look at user U2. And user U2 has given a rating of 3 here, a rating of 1 here, 3 here. And so in a different way, we can say the ratings of user 2 are actually very similar to U4 in that he has equally liked item 3 and item 5. Just as user 4 has equally liked item 3 and item 5, even though U3 had liked item 5 more than he liked item 3. So there is a discrepancy in a way that we can see here between this idea of similarity based on cosine similarity that we use. Another interesting metric that we haven't talked about yet is the average user rating. We have to recognize the fact that the data that's being generated is crowdsourced. And for those of you who are academics, I'm sure you've heard of, your users saying that one professor is a much harder marker than another professor. The same is, of course, true for rating of items also. So we could actually, by looking at the average rating, we could say that these 3 users seem to give, on average, higher ratings to movies compared to these 2 users because they have a lower average rating. So now what we are seeing is something even more interesting, right? We are seeing that this person here, in general, gives lower ratings, right? And so if we upgrade these ratings or move them up to match them with the same rating scale as this person, now that commonality in rating is actually becoming even stronger, right? Because what we are saying is a rating of 3 by user 2 is more like a rating of 3.3 by user 4, because user 4 always gives higher ratings. And so to deal with what is referred to as a user bias here, the rating scale being different for different users, what researchers did was to create a new metric called the adjusted cosine similarity. And here what you do is you subtract the average rating from the rating vector for each user before actually calculating the similarity. And because you have taken out the average rating, so for a particular user, that should be A. For this user UA, whenever we are predicting the ratings now, we are actually taking the weighted sum of the adjusted vector. What is the adjusted vector? Where we have mean scaled the vector. We have subtracted the mean out from the vector. We take the weighted sum of that. And so here we then add back the UA. And by making this adjustment, we can see now that U2 is considered to be more similar to U4. And we now have a change in ratings because we are now basing our rating with a stronger bias towards the rating of 4 here. So the rating we had here has gone up closer to 4 compared to what it was here, right? And that seems in line with the fact that this user U4 typically rates higher than the user U2. Now, we've looked at user-based collaborative filtering, where for a user that is our active user, we are looking at other users that are similar. We can do the same, but looking at items instead. And we call that item-based collaborative filtering, where we are now saying that for the active user, we want to know what will be the rating out here. We don't know RKJ. Now, instead of finding the neighborhood of the active user, what we do is we find the neighborhood of the current item that we are interested in predicting for. So again, we have now items in, these are U1, U2 through to UN. So each item is now in an n-dimensional space, again, a vector. What are the vectors? They're going to be the ratings given by all users to these movies. And so just as we had done for user-based collaborative filtering, now what we are doing is we are comparing this item that we want to come up with a rating with other items that actually have been rated by user UK, right? And we find now a similarity between these two neighboring items of IJ, and we follow the same process of taking the weighted sum. So here, what we will do is we will take 3.5 plus 0.9 divided by 0.7 plus 0.3. We would end up with a rating of 4.4 for this movie. And 4.4 seems right. Why? Because this movie is closer to this and has a rating of 5 compared to this one that has a rating of 3. Okay. Sorry, there's some background noise. Can everybody just mute? So in item-based collaborative filtering also, we are doing our mean adjusting of the rating vectors. Sorry. There's some background noise. Can we mute them possibly? Okay, I can. Right, and we are now able to compute, just as we were doing earlier, the ratings for a movie based on item based collaborative filtering. Now, I skipped over this, but there are some disadvantages, right? We talked about the new user and new item based collaborative filtering, and both of these are referred to as the cold start problem. So whether you're a user or an item, if you haven't rated, then you're not going to be able to get any recommendations, right? Other problems that we've kind of touched upon is the sparsity of ratings, right? So very often the similarity between two users is based on a very small number of items, and that might lead to inaccurate estimation of similarity. The big issue that we talked about of a new item being introduced, if an item is introduced at time t0, if it can only be recommended in time tk, then this time period is what we refer to as the item latency. And so with collaborative filtering, this latency can be quite high. And then a final problem that we haven't really addressed yet is the fact that we are treating all items to be equally important. Now, some items, like Spider-Man, has to be loved by everybody, right? And so if I have a similar rating to another person for Spider-Man, which is a 5, does that really mean that my interests in movies are similar to that other person? Probably not, right? So what we are saying is that some items are not great at differentiating between individual users, and so they should not be given the same weight when calculating similarity between users, especially when we already know that the number of ratings we are basing our similarity calculation on is small, right? So if I have the same rating in Spider-Man and with another person, but I have no other items that I have rated with them with a similar rating, then I should not be considered similar to them. Now, given all of these problems, the state-of-the-art mechanism for doing collaborative filtering is a mechanism called matrix factorization. And this is kind of like magic, right? I mean, what we have here is observed ratings. And as we said, we have a lot of sparsity, right? So we have missing data here. The idea of matrix factorization is the fact that you have users, and these users have given ratings to a set of items. But as we had observed here, these ratings are not given in a bubble. They are driven by some preferences. But those preferences are not recorded, because typically if you ask a user, why did you like that? And you start asking them too many questions, they'll stop giving ratings because they don't want to have that drudgery of giving you information, right? And so these preferences can be thought of as hidden variables, right? And these hidden variables are somewhere behind the scenes causing these ratings to occur. So the question that arises is, can we, now that we have lots of observed data of ratings, can we find these hidden variables? I'm showing two hidden variables, but what are these hidden variables going to be? There can be any number of them. What we are hoping is that these are the hidden variables, the preferences of the user that drove these ratings, right? Now, there are many terms that are used for hidden variables. You may have come across factor analysis in statistics, where we say that, yes, I have data that has x1, x2, and x3, but actually x1 and x2 are highly correlated, suggesting that there is some factor here that is causing both of these to behave the way they are, right? And this factor is not observed. So we also refer to these as unobserved variables or hidden variables. And in a way, when you think about neural networks and their hidden layers, right, where our first input layer is our observed data, our output layer consists of our output variable, and then we have these hidden layers, as you've learned, right, during this course. These hidden layers are actually also the same concept, right? These are some kinds of transformations that we may be doing on our inputs that are giving us a better representation of the data, so that finally we can do a simple classification here, right? Even using a linear decision boundary. Okay, so hopefully, I'm hoping that all of this is kind of making sense, right? So now what we are saying here is that if we knew the preferences of the user and we knew the ability of items to satisfy the same preferences, ability to satisfy those preferences, then we can represent them as a n by k matrix and an m by k matrix, right? Here we are saying item 1 has the ability to satisfy people that have a preference for H1 greatly, but not people to who have a preference for H2. Tim here may have a strong preference for H1 and a lesser preference for H2, right? So we have data in here that would tell us or give us a representation of each user with respect to the preferences. Now, we don't know these preferences, of course. And when we don't know something, what do we call them? In machine learning, we call them parameters. So how many parameters do we have in here? We have n times k plus m times k parameters, which is m plus n times k parameters. And the idea is that if we can learn to fill these numbers in such a way that we can reproduce the observed values here fairly accurately, then it will give us a belief that these can also be used for filling in these numbers, right? So what do I mean by that? Let's say we did some magic and learned these numbers in here and here now. So our parameters have been learned. These are our optimal parameters, parameter values learned using ML. Now what we are saying is we can call this U and we can call this V, and this here is computed as our predicted rating matrix, which is U times V transpose. Right, so this here is an n by 2 matrix. This here is an m by 2 matrix. UV transpose would give us an n by m matrix, which is what we had here as well. So this is our observed ratings. This is our predicted ratings. But now by magic, we do not have any sparseness. We now have numbers that have filled in all of the missing values out here, right? All of them. And how do we know this is a good approximation? We start looking at this. So here we had a 2, here we have a 2.1, not bad. Here we had a 3, here we have a 2.93, again, not too bad. We have a 3.78, we had a 4, okay, there's a little bit of an error here. Similarly, there's a small error here, and small error here, and small error here, right? But in general, we can see that the behavior is actually quite consistent. We are off by approximately 0.1 or 0.2 on most of our predictions, right? Look at this one here, right? And so what we have is a very standard machine learning problem that we are solving. We have a set of parameters that we needed to learn. We need a cost function. What is that cost function going to be? Sum of squared errors. And if you look at what we are doing here, we are not doing anything different from what we had learned in high school, right? Or even in primary school. That given a number, let's say 27, given that number, factorize it, right? So we can write it as 3 times 9. The only difference is that we are factorizing a matrix here and coming up with a user preference matrix. And this is an item preference matrix. And what are we learning from? We are learning from all the regularities within this data. So implicitly, what we are learning is that Paul liked item 3 and item 5. And Peter also liked these 2 movies, so their preferences must be similar. And Tom, who also liked these movies, must have similar preferences to these 2. So by looking at multiple ratings across multiple items, we have been able to come up with some regularity, some patterns in the data. And we have learned these preferences in such a way that we have been able to minimize the sum of squared errors on observed ratings. So we have essentially taken our rating matrix. We have approximated it as the product of 2 matrices. That should be transpose here. And P and Q are N by K and M by K matrices, where K is the preferences or interests, right? And we need to decide the number of K. How can we do that? You have obviously already learned, I'm sure, about hyperparameter tuning. and the use of cross-validation to learn these hyperparameters. Well, K here is a hyperparameter, right? And so we will learn this K by trying different values of K and looking at how well our P and Q matrix are able to predict ratings that have been hidden away when learning the actual parameters, the P and Q, right? Now, again, I don't know whether this has been covered in other talks. I hope it has been, but this here is the regularization term, regularization term. And what do we do in regularization? You've seen this hopefully when ridge regression was taught, right? Where you were saying rather than just having the ordinary least squares, I'm adding in some constant times. Oh, let me not call it beta, some constant times beta I square, where I goes from 1 to n, where n is the dimensionality of the data. So we are doing the same here, right? And the idea here is that we only want to make coefficients non-zero whenever they have a good impact on the error. The error gets reduced. So this becomes our cost function, where we are doing essentially a search in the space of all possible values that can fit in P and Q, and we are minimizing this particular cost function. Are there any questions on this? Now, this is something that most people find quite amazing. It seems like a very different type of thought process here. But the idea of matrix factorization is used all over the place right now, right? You've probably heard about embeddings, right? Word2vec, an alternative to Word2vec called glove. Hopefully these have been covered by other speakers in text analysis. What we have created here is really an embedding for users. Users that were earlier represented in 6-dimensional space are being now represented in 2-dimensional space, right? So we have gone to a lower dimensional representation of the users. And here is an example, right? So this is a data set that you can download yourselves. It's called Movie Lens. Remember, I had talked about John Riddle and his group called Group Lens that were the inventors of collaborative filtering. Well, when they were working on the collaborative filtering algorithm, they actually created a benchmark data set. And as you know, benchmark data sets get used so much that they lose their shine, but Movie Lens has also been used a lot in recommendation research, right? And this is a data set that is one of the smaller data sets. They have larger data sets in Movie Lens as well. You can search for it and download it and try out matrix factorization and all of these algorithms. But here, it has 610 users, 9,724 movies, and 100,000 ratings. Right, and the data set looks something like this. You have a row for every user and a column for every movie. And here you can see that user 1 had not given a rating for movie number 2. They also do have content about the movies, but as you know, this has not been used within the collaborative filtering algorithm. But it's still, I've put it here so that we can actually observe what these movies are. So very simply, running this algorithm, this Python implementation of the algorithm written from scratch, not using any libraries, right? Where we mapped every user and every movie onto just 2 dimensions. You can see that it's not very accurate, right? So the ratings are different. Here it's 4 and 4, and here I'm predicting 5.04 and 4.29. But still, it's not bad, right? Given that we have squashed down 9,724 dimensional representations of users to 2-dimensional, right? And we were still able to predict that the second movie would be rated 4.32 by user 1. And what was that movie? It was Jumanji. And if we look at the genre of Jumanji, the first movie that was liked by this user and the third movie are Toy Story and Grumpier Old Men. And here you can see in Toy Story, there's adventure, children, fantasy, which is exactly the same genre as Grumpy Old Men, right? And so you can see these similarities coming up here. Now, what I've shown here is the reduction in value of the cost function through iterations, right? So we are using gradient descent, which is the most commonly used optimization algorithm within machine learning, where we start off by random values being assigned to P and Q, and with every iteration, we optimize those values, right? And we are going from a value for this cost function of 12.65. After 100 iterations, we have had a huge reduction to 1.19 here. And what does gradient descent do? I'm hoping that you have seen this before, because we're coming to the end of our time here, unfortunately. In gradient descent, the basic idea is that you are trying to optimize some function, right? So you have a contour plot here, and you might start from a random value here, and you are essentially calculating the direction to move in that will give you a maximum reduction in this value of this function, right? So we're basically saying we have x1 and x2, which are our parameters. Let's call that beta 1 and beta 2 to be exact. And we want to find that direction from where we are currently, which is a random starting point, from where we are going to get maximal reduction in our cost function C, right? And this is the minimum, the global minimum that we are showing in this case, because this is a convex optimization problem that I'm visualizing here. And how do we find the direction to move in? We calculate the gradient, right? And what is the gradient? It's the partial derivative of the cost function with respect to beta. So what are our betas here? Remember that for every observed rating by user U of item I, we are predicting it using our Q vector and P vector, right? And so our beta here, we are basically calculating the partial derivative with respect to PU and the partial derivative with respect to QI, right? And so what we are doing here in gradient descent, typically when we have some data, we take all the data and pass it through, right, our predictions. We calculate the overall cost and then find the direction to move in. In stochastic gradient descent, instead, because if we have very large amounts of data, every move in this space, right, every step that we take in this space that we are trying to do our optimization in, that step is going to be very slow if we are using 100,000 or 100 million data points that we are trying to optimize over. So with stochastic gradient descent that is used here in matrix factorization, what we say is we will calculate the error for only one cell at a time. So what is the error in the rating that is predicted for a user U on an item I. And we are going to use that as our estimate of the partial derivatives and update our Q and P values. So notice here that this here is only one cell in our rating matrix, right? This is user U and some item I here that we're calculating the error on. But we are updating all of the values in P, right? So for U. So this whole vector is getting updated, and so is the whole vector in Q for the item I, right? So we are updating these complete vectors, and when we multiply those, of course, what's happening is we are updating all of the predicted ratings in these spaces here, right? Now, one of the problems here is that when we are doing stochastic gradient descent, now that we have P and Q that are both parameters and the prediction is the product of these two, we do not have a linear function. And because we don't have a linear function, and we essentially, this means that our sum of squared errors is not going to be a convex optimization problem, we have a chance of getting stuck in local minimum. And so, one of the algorithms that's a tweak on stochastic gradient descent is the alternating least squares, which says that at any one time, we will only optimize Q or P. And so at any one time, we are looking at this as a linear function based on one of these being assumed to be parameters and the other to be constant, right? And so we take a number of steps using Q as constant. Next, we now change alternate across to P as a constant, and we take steps in that direction. And so in each of these sub-optimization problems, we have a convex optimization that is taking place. That's known as the alternating least squares problem. Now, a number of years ago, and I will just finish, unfortunately, I won't have time to go through all of this, but a few years ago, Netflix came up with $1 million prize, where Netflix said that anybody who can create a recommender system that reduces the root mean squared error of my current recommender system that's predicting ratings for users by greater than 10%, they will win $1 million. So that's a lot of money, and it was a lot of money, especially at that time, right? This I'm talking about is probably around 15 years ago, if not more. And so a lot of the researchers started building teams and working on this problem, and the winning team, actually what they did was very interesting. What they did was they said that the rating for a user should be broken down into 4 parts. One is the average rating given by any user to any item. The other is the item bias. So just the fact that, remember we talked about everybody loves Spider-Man, is the same idea here. So the item itself will have a bias that it creates. So if it's a positive bias, that means it's like Spider-Man, everybody rates it higher than the normal, then that's what this RI represents. Similarly, we have a user bias. And finally, there is a component that says the user's consumption of this item has an impact on the rating that the user gives it. So here what we are saying is, say on average, people give a 3.4 rating to a movie. Derek is a harsh rater, and therefore we give a negative user bias to Derek. The movie is Star Wars. Everybody loves Star Wars, so we give it a positive rating. And Derek's interaction with Star Wars, because Derek likes science fiction maybe, or for whatever other reason actually liked Star Wars, we give it a positive contribution to the final rating as well. So the final rating by Derek for Star Wars becomes 3.4, which is the average rating. Then we add 0.8 because of Star Wars, take away 0.4 because Derek is a harsh rater, and add in that rating that Derek actually liked Star Wars. And so we end up with a 4.3 rating from Derek for Star Wars. And all this is doing is, it is now creating a more complex cost function. And this is the last slide, Dr. Jyoti, so we can end after this. But this cost function here, we are now saying that our prediction is the mean BI plus UI plus the matrix factorization of only the interaction term, right? And so the predicted rating is this here, where mu we can of course calculate simply by taking the average of the million ratings that we may have. But all of these are parameters that we need to learn, right? And so we are essentially updating all of these parameters now within our stochastic gradient descent. And the regularization term is now got the sum of squares of all of these parameters rather than just P and Q, which is what we saw in the original matrix factorization. Okay, so I'll stop here. You know, I think collaborative filtering is the more interesting space compared to other spaces. And then matrix factorization is a very important part of collaborative filtering. I hope you've kind of got a flavor, at least, of matrix factorization and what it is about. And, you know, I can provide resources if you want to actually consume more on this subject, because we have a lot of content on that. But for now, I shall stop and hand back to Dr. Kiran. And thank you for giving me the opportunity for speaking.
Thank you, sir. Participants, any questions? If you have any doubt, any question?
Okay, doesn't look like it.
Okay, yes, sir, thank you very much. You have really made it clear to students and even to the participants, those who are working into this area. It will be very helpful to them. And for participants, there is information for you with collaboration to Sabudh Foundation under the guidance of Dr. Sarabjot Singh Anand. We are again running one STTP on data science and its applications in collaboration with the Department of Computer Science and Information Technology, Guru Nanak Dev Engineering College, and Sabudh Foundation. So participants who are interested, they can, if they want to take more use of sir's expertise, so they can enroll for that course also. I think it is totally handled by sir, and there are eminent personalities sir has arranged for us. So it will be very kind of you, sir. You are organizing this event in our institute for our students and for our faculty, and even faculty from other institutes all over India. We have circulated it to participants also. If they want to, if they're interested, they can enroll for that course also. Sir, your talk was really wonderful, and you have spared time. That is really so nice of you. Parminder sir told me you had your prior engagements, but we wanted you at 2 o'clock, but you were not available today at 2 o'clock.
Unfortunately, I have a packed day today. So we actually run a webinar series also in Sabudh. So every Saturday at 11 o'clock, in fact, those sessions start. So we pushed back today's session to 11:30.
Even Dr. Sujit has told me that sir had prior engagements. So anyway, sir, thank you very much. You have spared your time. Thank you.
Thank you. Thank you. Thanks, everyone.
Okay, sir. Thank you.
Okay.
Participants, next session will start at 11:15, and it will be again continued by Dr. Mani Madhukar. He will be delivering hands-on session today. in continuation to the previous session, he has given the theoretical part on that day. Today he will be delivering the hands-on session. So kindly be there at 11:15. He will be starting the session at 11:15. So we'll have a break for 10 minutes, then we'll start again.
Okay, ma'am, thank you. So we'll again join at 11:15. For one more interactive session. So I welcome sir again on this STTP.
Thank you, sir.
So should we start, sir?
Sure.
Or
Give
should
me
we
a
wait for
moment.
5 more minutes?
Yeah, we'll wait for 5 more minutes, sir.
Okay, sir. Okay. Thank you. So, sir, I think we should start now.
Sure, sir.
Sure. Thank
Okay,
you.
good morning, everyone. And before I go further, look, I want to get some feedback. Because that will depend upon what we will do today. Now, I want you to actually put on the chat window whatever you have, whether you have been able to install the software, whether you have been able to get access to IBM Cloud, because whatever you put on the chat, based upon that, I will be able to do the hands-on which I'm wanting to do today with you, right? So this session is aimed at doing some hands-on activity using, IBM Watson Studio, either on the desktop version or anything else, maybe on cloud. So, please put on chat whatever you have been able to do, right? Whether you have been able to get access to IBM Cloud, Academic Initiative, were you able to download the software, the one that we discussed in the last call. So I'm looking for your feedback on the chat, please. Please let me know what have you done in the last 2 3 days since we met, or have you done at all or not. If you're not done anything, just put that as well, right? Not done anything, not installed anything, or not registered for AI portal. I'm waiting for your messages on the chat, because what you tell me, based upon that we will carry forward this session. Okay, if you have installed something, I will actually I'll make you do some hands-on. um okay, I'm just seeing a few responses. Resolve it for you. I want to ask whether you have been able to register for Academic Initiative portal, and have you been able to download the Watson Studio from there, and also if you are able to register for IBM Cloud. Okay. Please put it on chat, okay, so that I can see where we are. Okay, I can see a couple of messages here. So I told, for people who are getting a message that the college is not yet registered, I asked you to, update the details on a link. See, it's still there on my slide, where you could have added your college name there. Okay, the free bit would not actually, make sense for you. This is an entire license, right? So that was not the case. Okay, the download was not getting completed. I hear that, but yes, it is a bit heavy software, but then it has a lot of components into it intervened, so it will take some time for sure. And in case you are on a in a lean network, it may not be, it will not actually do. That's the reason there is something called as download director, which is available on the website. It is the same as, it's the same as, that earlier we used to have download accelerator and all, right? So even if there is a partial download, if you would have downloaded with the download director, it would have continued from where it left, right? So download director would have been a more appropriate choice. For those who say that their college is not registered, I told you to put the college name in the sheet which I've given you. Remember the bit.ly link which is still visible on the slide? I told you to actually put a request for adding the college there. I haven't got any request, by the way. Neither the smart interns mail IDs, anybody has raised requests, particularly from your session. So guys, I want you to, really respond to it. This session is hands-on, but then unless you don't have anything, then how will we do a hands-on? Put that on the chat, whatever issues you have, and I'm going to resolve it. And then I'm going to continue with the session today. For those of you who are facing a challenge with the download, please try to download it with a download director. It is more like, whatever times the download breaks, it will continue from wherever it broke. So that way, download gets completed and it's taken care of. Okay. Second is, yes, it's a bit heavy, so it takes some time to download. There is no denying that fact. Okay. Third is, for those of you who say the college is not registered, I told you to put the college name on the bit.ly link there. In case the college has given you a institutional email ID, this was the link that you should have actually, put your college name and the email ID there, right? In case the college does not give you any email ID, then I asked you that you can come and you can request for a link over this Smart Interns mail ID. This would have helped you to get access to AI portal, and then you could have downloaded the software, the courseware, or whatever you wanted to. Okay. Okay. I don't see any more responses here. So, guys, I need to understand from you that if not, then we will continue with the theory part in this session, which I don't want to do. I actually want you to do some hands-on. It's really important to get hands-on skills, right? Just not this theory part will work for you. Okay, I'll come back to this chat window again. Those of you who are not conveying to me that where you are, please put your, whatever is with you on this chat window. Anybody who has got access to it, anybody who has got downloaded, please put that on this chat window as well. Okay, and then I will take a call whether I want to go with which sort of hands-on do I want to actually go along. In the meanwhile, I'll get started with the session today, right? Just to for the in the interest of the time. So this is what I really wanted you to work with you today. I am not sure if we had a chance to have a discussion on this. I'll skip a few slides, which we might have already discussed some point. Okay, yeah, this is a typical problem that any AI ML guy will actually find, right? Any researcher who is doing any work in artificial intelligence or machine learning or some similar thing where we have a model building, where we have a prediction to come up, everybody will be able to relate to this slide. So normally, how does the process start, right? From a researcher's point of view, let's try and understand. Okay. The first thing that a researcher always tries to look forward is get a domain, a problem domain. Okay, let's say I'm just sort of picking a name, just to give an illustration and example, right? So let's say I'm looking for a smart grid. Okay, for example. Okay, so let's say my domain is smart grid, and I want to do some research around smart grid. Okay, great. So the next thing that I'm really interested and I will need is, do we have any data sets around smart grid? All right. So that will be my next hunt. And if I have to need a data set, then I told you that on Academic Initiative portal, there was this data asset exchange where there are a lot of these data sets available. Anybody can go and download the free open data sets there. Okay, so second thing is I need a data set. Okay, so let's say I've already got a data set. I've been able to lay my hands. Maybe a smart grid from not from India point of view, maybe Australia, New Zealand, maybe US, Canada. Some place I've got some data. Okay, there is a lot of data available, by the way, in this domain. Okay, great. So I've got a data. Now, third thing is I need to analyze this data with some machine learning techniques, right? So if that is the case, then almost like what if I'm actually wanting to go with a classification approach, right? So there are almost like 30 broadly there are 30 algorithms which I can make use of, right? So right from a naive bias to a logistic regression to a LGBM to a gradient boost tree to a decision tree, to something like a support vector or a SGD or a random forest. And there's so many, right? So let's say I have a data set. I have got 30 research. I have got 30 algorithms as well, which I want to try and put my data set on, and then I will be able to actually get an outcome. Once I get a result with a certain algorithm, I'll try to compare that result with some other algorithm so that I identify which one is the most appropriate algorithm for me to go ahead, right? Which is the most suitable one, which gets me most of the desired accuracy to me, for getting started. Just a moment. Okay, yeah. So, so now that I have these 30 algorithms to actually test my data set with, so after doing all that, maybe a month or two or three, wherein I actually, implement all these algorithms programmatically, and I, put my data set to use with them. And then I will be able to identify, okay, let's say gradient boosted tree is maybe, gives me the best approach, right? Gives me the best possible outcome, right? As far as accuracy is concerned. Great. So what I'm going to do is I'm basically, once I have actually able to identify my algorithm, the next thing is I'm going to deploy that, right? So I'll deploy that particular model, and I will, make it open to others to test the data with that model. Okay. So great. So far it's all going great, right? So I've been able to deploy my solution, my model, and I'm going to really now test it. And you know what? Then comes the next problem, right? Where people, or rather, with different varied data sets, when I try to actually test my trained model, what happens is the amount of, maybe overfitting, underfitting, maybe, the type of output that I'm getting with this test data may not be the one which is that I'm looking forward to. Okay. And you know what, that is actually the worst moment where you actually get to do the entire rework again, the entire strategy, right? Maybe you'll again go back to the drawing board, and you will again start identifying, okay, maybe gradient boosted tree may not have been the right approach. Okay, what was the second best approach which I was there? Let's say, okay, let's say it was a XG boost, right? Now you'll again pick the same route, where you'll again train the model with the XG boost, and maybe bring in a few more sampling techniques on top of it, make it more hybrid, to give it that novelty that you want to have as a researcher, and then again deploy the model, and the entire cycle actually goes on, right? Which is again the same time consuming pattern is going to kick in. It will take some time, right? So if you try to understand this, let's quickly jump onto a slide which I wanted to talk to you about, right? This was the one, right? So according to one of these surveys of Forbes, right? So people or data scientists actually spend 80% of their time only on data preparation, right? And it is, you can very well understand with whatever we discussed so far, right? Compared to that, the building, the building, the training, compared to that, training the model or deploying the model, or even other bits is really very, very less. So if you see that breakup of this at 80% of the data time, right, for data preparation, almost 60% is towards cleaning and organizing the data, right, which is really humongous over the overall effort we're talking about, right? Almost what a two-thirds of that overall effort is only put on the data cleaning and organizing of the data, and then the remaining kicks in. So this is where we were discussing the other day, right, about auto AI, right? And how it really helps in typically managing the life cycle of a particular project. I'll come back to the chat, guys. Whatever you have done, you have downloaded or you have not downloaded, please put that on chat. Based upon that, we'll take a call that way we go from after discussing this. Okay, so let's try and understand what's the reasons typically of this. So we just talked about 80% of this time, right? That means once you take care of this data collection, data cleaning, all this effort, that means as a researcher, you have a lot of more time at hand to do something more productive, right? To do something which is really more aligned to the type of research that you are looking to do, right? Okay. Second is to do a research in AI ML segment. You don't only need one skill set. You need to have multiple skill sets in place. You need to know statistics. You need to know artificial intelligence. You need to be an IT guy. You need to also be conversant with various data wrangling techniques, right? And you also need to have a domain knowledge, right? We were talking about this smart grid data set, right? Unless you're able to figure out the data, you're able to make sense from the data. How will you actually be able to analyze this data, right? So it's really important, right, that this data that you are basically talking about is something which is able to you're able to make a sense of it. Okay. And unless that happens, right? So okay, let's see the next thing, right? Unless that happens, you will not be able to think about or do some productive work with the data set that you're working, right? You'll keep on going back to the same loop as we were talking about, right, a while back. Okay. And this is exactly more important. Once you have trained the model, and maybe you have deployed the model even, when the model actually goes into the production, it has to be regulatory compliant, right? It has to comply to various regulatory guidances. And that's where, right, the trust and transparency actually comes into play, right? You have to monitor the outcome that your model is generating for explainability and maybe for biasing. I'll give you an example there. Some time back, right, US had implemented a payroll a system which was AI enabled, which was supposed to help the judge to take a decision whether a particular a person should be granted payroll or not. Now, what this AI engine did at the back end was, it basically, was trained with some data set, and then it also ingested some data set on the fly, right? And once the judge was hearing up, a payroll application for a particular person, this model will actually make the suggestions based upon various n number of parameters which are already put in the system for the person who is seeking a payroll, right? And you know what, after a certain number of years into the use, what was discovered was this system was actually heavily biased. This was heavily biased for two people, of different race, of different creed, based upon various parameters, that it always gave a skewed decision or a skewed suggestion towards one particular race compared to, it would actually give. So it was not fair, right? So that's where the entire thing of fairness in AI and, the unbiasedness in AI actually, kicked in. And it's really very important now. So whatever system that you are creating, it needs to be governed by some regulatory constraints to enable that the system is, it's no more a black box. AI should no more be a black box, because everybody questions, right? And when somebody question, you need to have a rightful solution to that question, right? So that's why. So that monitoration or the explainability is also actually a must thing with that, right? Yeah. So this is again important, right? Once you have the deployment done, how do you actually keep the model updated, right? So this is again a reason, and that's the reason why AI auto AI service that we discussed the other day really makes a lot of sense from our overall life cycle management, because it automates the data preparation, it automates the model development for you, it also takes care of the feature engineering and hyperparameter optimization, right? And this is in a nutshell basically you play with, right? So as a researcher, as a ML researcher, you basically play with all these 4 5 things, right? Data preparation, model development, feature engineering, parameter optimization, and this ultimately leads you to a better accuracy, a better, a recall value, whatever, right? So that's what, right? So this is AI lifecycle management we were talking about. I'll again take a small pause here because I want to understand if there are any questions, or have you been able to, complete the download, or do you have access to something now, right? Because if you have access to it, then only we'll be able to, sort of work. Okay, I don't see any more responses on the chat for me, guys. Um, so I'm not sure how will we do the hands-on. The entire idea of doing this session today is to do a hands-on. But in case not, then maybe I'll just show you some demo again, and maybe I'll just talk to you about a few more things. Okay. Okay. So I'll dig into more about auto AI, because in last conversation we talked about Watson Studio, right? And we talked about Watson machine learning. Now, auto AI is actually one of the services on Watson Studio that we are talking about, right? And this service is primarily aimed as automation of AI development. Okay. Now, AI is in itself automating some processes, right? But auto AI basically provides you a layer on top of that, so that AI is utilized for doing AI for AI, right? That's what is the gist here. So whether you are designing something using AI, right, you use AI. Whether you are optimizing something using AI, then again you use AI for that, and same goes for governing as well, right? Yeah. Okay. I'll skip a few things. We just talked about that, right? But this is a typical flow, right? Particularly from our auto AI model point of view. Maybe we already discussed that the other day. You have a raw data set, right? You have a raw labeled data set, right? And what you're going to do is you basically, upload this particular data on our auto AI service. which basically prepares this data with, doing a selection of feature type, will basically imputation of at various levels for the missing values, right? It also does a feature encoding and scaling, right? So it on its own, it basically finds the best pre-processing, imputation, encoding and scaling strategies for the data set that you have provided to the service, right? Once we have been able to actually, get the data prepared, the second thing is you are going to select the model, right? You basically find the top k estimators from a set of almost like 30 algorithms, right? And once you have that, right, then you basically do the hyperparameter optimization on those selected estimator that you have found, explored and you have identified. Okay. What it really helps is it basically helps in creating those and modeling those pipelines, right? The 7-8 pipelines we saw the other day, right? And once you have those pipelines defined, the next thing that you do is you basically do a feature engineering, to find the best data transformation sequence, right? Because you want to achieve the best possible accuracy, and to actually get the accuracy, you play with a few things, right? Hyperparameter optimization, feature engineering are two major things that you can really tweak the model with, right? And in case you are able to, sort of, able to get some better transformation sequence using a feature engineering approach, then you again do a hyperparameter optimization on that particular estimator. You do a, after the feature engineering approach, you do again a hyperparameter optimization, and then you really see that whether this model is good to go. And then if it is the one, then you save that, you deploy that, you can even deploy that as a web service, right? I told you the other day also, the model which is getting created using Auto AI or Watson Studio, and in Watson Studio, you can publish that model as a web service. What it means is the web services that can be used in your research paper as well, right? That you have published the link, right? So that link can really lead the other researchers to actually have a view of your work, the web service that you have published. They can even consume the web service with their own data set, right? So let's say there is a similar data set that is available by some other researcher, and he wants to quote your work. So you can actually use that web service to test his data set with the model that you already published, and maybe quote your research paper and quote the data that he is actually, results that it is getting from your model, right? So something like that, right? This is what I really wanted to do today, in case you would have downloaded and you would have installed the Watson Studio software. You'd have gained access to IBM Cloud, but I don't see that sort of outcome coming from you guys, right? So we'll not be able to do hands-on, but then this is what I really wanted to do today with you. Giving you a complete drill down into Auto AI so that you can publish your trained models, so that others can consume that in their research papers. And I already showed that those comparison of algorithms with you, so you could have used that in your charts, in your research papers, those charts to actually utilize and make the papers better. Okay, I'm seeing a few discussions, a few messages on the chat. I'm not sure, Divya, when have you put the request for registration, right? It takes some time, but that's the reason I had done a session on 4th. And, the idea was between 4th and 7th, if you'd have done the registration or put the request on 4th, by today, you would have actually gotten access and you would have already downloaded it, because 5th or 6th, we have already cleared it. Makarand, you actually download it, but once it is installed with using Academic Initiative portal, you actually get a 1-year license. Okay, and that license actually gets renewed after every year. So whatever software you get on Academic Initiative, they come in a yearly licenses, whatever, whether it's SPSS Modeler, whether it's Watson Studio, Desktop Edition, whether it is I2 Analyst, or anything for that matter. It basically comes a addition in a 1-year licenses thing. After 1 year, you can again generate a promo code. You can again generate an authorization code to extend the license for another 1 year, and so on and so forth. So this is how it actually goes. Okay, so let me go further with what I was talking. This is really a cool way, for our researchers to really, leverage and pursue and maybe make things work for them. Okay. So the other day we talked about it. Maybe I can show it again in case we have a few more new people on this session. We are going to use a Watson Studio service, right? The Watson Studio service is using an object storage at the backend. Okay. Now, what this object storage is doing, this object storage is holding the data set that you have uploaded, right? So remember in the Auto AI service, the service asked you for a data set. Where is the data set? So the data set that you upload actually gets stored in this object storage, okay? And after it is held up in the object storage, the Watson Studio reads the data, and the Auto AI service, which runs on top of Watson Studio, basically identifies the data, the schema of the data set, and comes back and asks, on which field do you want to do a prediction, right? So we gave one field, and you can give any other field right there, right? Now what happens is Auto AI service under the hood uses Watson machine learning and Apache Spark, right? Um, so this Watson machine learning basically, provides for all those machine learning algorithms, all those models that we were talking about a while back, okay? And then this gets published as in form of a data, in form of a web service, or in form, you can even publish that as a notebook. We saw that the other day, right? So the entire code which gets created using WML and Auto AI gets populated as a notebook, and you can replace, the system has a provision of providing a replacement of the Watson machine learning with the open source like scikit-learn, sklearn, all these libraries that can be actually used in the notebook there, right? So this is what is the typical architecture diagram that I wanted you to work on today, and we would have together made it but then I don't think that we can do the hands-on today now because you haven't been able to download and complete the installation here. Well, I thought we will do a hands-on, and that's why I thought this is what we are going to do today. So I thought you would have already downloaded a Watson Studio, and we would analyze the data using either Jupyter or Python or maybe RS Studio in some way. Okay, since we are not able to do that, we'll skip that piece now. Okay, I'm going to take a pause here, guys. And if there is any question, I'll ask you to unmute yourself and ask it. Please feel free to unmute yourself and ask. Because me just talking will not make sense. This is not what I intended with this session. I wanted this session to be hands-on so that you can play with the tool. You can actually taste how how do you get the outcomes and all that stuff.
Hello.
Yeah, go ahead.
Hello, sir.
Yeah, go ahead, ma'am.
Would you please show the hands-on today itself so that after we will be able to download it, we can practice later on by ourselves?
Yeah, but then that will not happen the way, who has completed the installation? I was asking for last half an hour almost. Nobody was writing it on the chat, right? You
I
yourself
had
are
completed
you are
the
yourself
download
teachers, right? Unless you when you are taking a class, you need to know that the students need to know, or you need to ask the students about where is the bottom line, where is the baseline, where do you start teaching from, right? Now, unless you share what have you done in last 3 days, 2 days, how will I get started with what I intend to do? Okay. Sumit, I could actually get all your messages, the one that you pinged me. So not sure. Anyways, I will show, some bit of it, but then you'll not be able to actually complete it, the way I wanted to. I really wanted to take you through the steps. Rather, I wanted one of you to share their screen and I would have guided you to do that. But now that can't happen. I thought I will ask one of you to share your screen, and I will give the instructions and you will complete the hands-on, and maybe others will also follow up. So that's what I really wanted to do, so that to make it more inclusive, but okay, unfortunately will not be able to do that. I'll quickly go to my IBM cloud account, and no, Pankaj, we are not looking for the Anaconda thing here. We were looking to work on the Watson Studio to leverage those services. Okay. Guys, we just missed an opportunity in terms of doing something meaningful today. And okay, anyways.
Hello, sir. This is Shruti here.
Yeah, Shruti, tell me.
Yeah. Sir, actually, we have a register for this IBM ID. Actually, our college has type with this IBM. Can I, download it from that ID itself rather than again registering for this, again accessing for it? Hello?
Yeah, I'm just trying to understand what you are trying to explain to me.
Yeah, when we went for this, the link, whatever you have given in a PDF, we have pressed for the test, trial it for free, right? Again, there it is asking your email ID become your, IBM ID, right? Already I have an IBM account. Already we have an IBM account. Can I download it from there, through that?
Do you have access to this website with that ID?
Yeah, we have.
Oh, that's what I know everybody was asked to do, right?
Okay. Then I'll try, but I didn't know about this is the same ID. We got it from our college. So I'll try it, sir. Wait, give me a 5 minutes.
Once the college gets access to this portal, whatever you register, that is basically called an IBM ID. There is nothing difference. Whatever, something at the rate gndc.ac.in, whatever,
Oh,
right?
sure. I'll try.
Anyways, so yeah, Makran, right? You will need to install SPS, this IBM Watson Studio from there, and then you can, go on from there. So I told you the other day as well, right? So all these software which are available is what I wanted you to leverage on, particularly this one and SPSS Modeler Premium. Both of them actually come in a license of 1 year thing. And these are all renewable licenses, right? Yes, so you need to sign in to this portal and then download. I don't think that was such a big deal to do, but now that we have gone beyond it, so let's try and check out something else. So this is how, it might have been looked, something like that, right? You only had to actually download the base package and then you could have, and that's why I also forwarded you the PDFs, right? Why do you think I would actually take the pain of forwarding the PDF in case, the entire objective was to give that comfortable feeling to you to actually start getting started, right? See, this was basically a step-by-step approach of downloading and installing. And when you actually, and it is clearly mentioned that it takes almost like 7.5 GB in all total space, right? So that's the reason 2-3 days were sort of provided. So once you install this, you basically are able to install the core package. And then you can also add modular and notebook support to it, right? Once you have installed the core package. So you're all technocrats, right? You're all people into technology. You teach technology. I'm not sure, right? Okay, so let me go further and let me try and see what we are going to do today with you. Okay. Okay, so what I'm going to do is, guys, I'm actually going to give you a link on the chat, which has the complete step-by-step approach of what we intended to do today. I'm giving you this link. You can copy paste from the chat here. No, there is no software for 32-bit OS. It's a 64-bit OS software which is available there, unfortunately. Okay, Gursimar, in case you have, you have downloaded the Watson Studio, yes, I would actually request you to, share your screen because I'll just stop sharing before I do that for you. Give me a second. So this is the other thing, SPSS modeler, which I was actually talking to you about, right? And maybe we already have seen a demo of this the other day, and I wanted to, make you do that today. Yeah, so you have this entire palette of tools available here, which had all these various, it had support for Python, it had support from Spark as well, right? So you can see all those XGBoost, K-means, multi-layer perceptron, for doing all those deep learning things as well. and you have this entire KD simulation, KD modeling, Gaussian mixture. It also has support for, auto classifier and all that stuff here. Yeah, if you see this, the modeling tools available there, it has auto classifier, it has auto cluster, it has an auto numeric prediction model for doing predictive analytics there as well. And you have all these various decision lists, linear tree, regression, PCA, neural net, feature selection, all of them which are I will use for modeling, and other things which are available here, which would have actually wanted you to use today. But now that I'm just sharing a link with you, you can do that on your own once you have been able to download and install this. Okay. I'll give you one more link before I go ahead and okay, this is another link. This is basically a link to do analysis on a telco churn, means in telecommunication company, right? So you keep on changing, vendors. So sometimes you are doing with Airtel, sometimes you are doing with something with maybe Idea and all that stuff. So how does telecom company, take care of that, right? So this particular um, prediction model works with that, which basically takes into consideration the telco churn. We call it as churn is basically moving from one vendor to other, right? And we do analysis for that telco companies using this code pattern. Okay, so you can try this as well there. So I'm gonna stop my sharing here, guys, and I would request the person who has installed their on the local machine to share it, and maybe I can sort of work with them to do something. So you can share the screen. Goldsimmer, you can share your screen, right?
Gulsimar, you are co-host now. You can share your screen.
Goldsimmer, you share the screen, then I will guide you through the rest that what you can do. I just want to show the participants that once you install and once you are able to finalize, how does it looks like? So they may see my screen, but then it will make a lot of sense if they see somebody from you doing it. Okay, great. So you have downloaded and you have installed the Watson Desktop Edition, Gulsimar. Allow access to that. Okay, now you'll have to log in into your, click on next and then just log in with the email ID that you have. So this basically connects the backend server to check the validity of the license. And then you can, so this IBM ID is the same email ID that you would have actually registered yourself with. Whatever you have registered, the same email ID. I even proposed, for those of you who do not have an email ID, from college, I had said that we can get you a Smart Interns mail ID for you to get access to it. So I had been sharing some links on the chat, guys. I hope you are able to. Okay, I guess I shared it with one participant. My apologies. I'll just share it with everyone. Okay, I'm gonna share this link here. This is what I was actually referring to, guys. And this was the other tutorial which I was actually referring to. These were the two, resources which I was actually looking to share. One is with the telco churn analysis of that, and other basically guides you through how to build a visually a model, with a visual aids.
Hello. Hello.
Yes, Kursima.
So, can you please guide me further for this?
Please mute yourself.
Yeah, I just got dropped. I've rejoined, sir. So you can now allow access to all that, right? Yeah, just give a project name. Let's say, right, prediction, anything. Just give a name there.
Participants, please mute yourself.
Say create, right? Okay, you just say, maybe later, just cross this, Golsimar. Okay, and help us improve. You just say may not at this time, and just that radio button you can close it. Just say no, not at this time, and then so that you're not prompted by these again and again. Okay, and then click on this project that you have just created. Great. You have downloaded a 30-day license pack, Golsimar. You're not downloaded from the AI portal.
Yes, sir.
You see on the left-hand side, it shows 30 days.
Oh,
You have not downloaded from the academic initiative portal with your email ID, academic email ID. You have downloaded a free trial pack here. That's the reason it is showing 30. Otherwise, it was shown 365.
okay.
Anyways, well, we are already too late into it. So you can actually click on add to project here. So if you see there right now, you can actually add some data base to the project. You can add a data refinery flow to this project, and maybe you can add a data connection as well, right? But this is not absolute. This is not what we are looking to do. Can you just cross this? And towards the left hand side of towards the left hand bottom under 30, scroll down. Yeah, click here. So, you are yet to install the modular and the notebook, which you have not installed. That's the reason SPSS modular is not coming there. This is a very powerful tool, guys. This is a combination of two very big software actually. People buy licenses for SPSS modeler. People buy licenses for Watson, right? And you are getting everything clubbed into together for you. So you're not actually understanding the strength or the power of this software. You're not getting it. Okay, it will take some time, ma'am. It will not just get up and running for you like this. It will take some time. Okay. So, you have to complete both of these, Nopid modular and notebook, and then you can follow the links which I had shared you. Can you maybe you can just minimize, right? There's no point getting into it. You will be downloading it. It will take some time to you. Okay. Maybe you can stop sharing and let me share the slides again. Then we'll not be
Okay.
able to do. This is not complete installation, no? Okay. Thank you. Sir, can you please enable my screen sharing?
Yes, sir. Yes, sir. It is enabled.
Thank you. Okay, so let me come back to, presentation that I was showing you. And so once you are able to sort of download and do all that stuff, right, you can add a lot more things to the project. Okay, guys, let me show you a few things. Okay, so if you see here, you can add a host of things to the project here. Okay, so there you were only able to see data connection, and other things there, right? But once you're able to download and you are able to add the modular SPSS modular and notebook, you will also be able to see the notebook and SPSS modular and other things there, right? Model from file and all. But with this service, you can also actually add a deep learning experiment, okay, for optimizing the performance of a neural network, and it provides it auto provisions GPU support for you, so you don't have to actually ask for it explicitly, but it comes along bundled with this experiment there, right? Similarly, somebody who is working on optimization problems, right, maybe any branch, doesn't matter, only computer science, it can be mechanical, electrical, electronics, because optimization is a area which almost every stream works with. Not just engineering, non-engineering also work with those with optimization problems, right? So for that, the Cplex engine is basically the underlying decision, the optimization power engine there, which can be used for building prescriptive models using Cplex engine. Okay. Yeah, I already talked about this, that there is a natural language classifier model which can classify the textual content. You can use that service there. There is a visual recognition model which can classify images, or which can even detect objects within the images using custom models that you can define and train. Uh, there is this data refinery flow, right? I told Auto AI can do all the data cleaning itself, right? But in case you want to create a pipeline for creating for cleaning your data, you can use a data refinery flow, which helps you create a step of ordered things for cleansing, shaping, enhancing the data, data set that you have actually applied to the system. Okay, so this is all this particular service can do. And this can also actually create beautiful dashboards for you without writing any code, right? For those of you who are not very conversant with the code, this dashboard can actually help you do that creation of the services there. Okay, so this was all about Auto AI. And by the way, I told you, did I tell you that Auto AI is just one part of the Watson Studio? Let me show that to you. So I am actually on IBM Cloud, and in the services section, I'm going to the machine learning services. Okay, there are all these category of services, right from compute, containers, storage, analytics, blockchain, logging, integration, IoT, security, mobile, and all. But let me, for the sake of brevity, I'm just going to AI and ML. So see, under AI ML, there are almost like 19 services here, right? And we are using Watson Studio, and even under Watson Studio, we are just using one service, Auto AI. So you can just imagine how powerful is this tool, right? When it actually takes into account all the services, all the things that it actually, all the power it offers. Not just this, there are other services like Watson Assistant to create chatbots. You can create conversational agents using here. There is a knowledge studio service which basically teaches the Watson about the domain, about the language of your domain. For example, somebody who is doing a research in biology, let's say, right? And then he wants to train the Watson to understand the biological terms, the meaning of them, right? So what the knowledge studio is basically can be used to do that. There is another service called Compare and Comply, which basically talks about governing documents which can be converted, and then based upon that, you can classify and compare various elements of a document. About language transfer. This is the other service, machine learning, right? This is the underlying engine of the Watson Studio, we called as Watson Machine Learning. it basically provides for a lot of ML enhancements as a part of the service, right? Okay, this is my natural language classifying classifier, and then this is natural language understanding, which uses NLC. Uh, this is another service of interest. What's a knowledge catalog? Yeah, this is really good, right? Which basically helps in discovering and cataloging content across different data sources, right? It provides you all of that together, uh, okay, and then this is for infusing that the transparency, that unbiased net, that traceability in the data model by using what's an open scale. Okay, so these are a couple of services which anybody can make use on IBM Cloud, and there are almost like 200 plus services available on IBM Cloud, guys. Okay, so this is absolutely free, right? uh, I'll go back to the academic initiative portal just to show you what I really mean to explain to you. See this? Uh, just like data science, there is another tab called IBM Cloud, right? On the IBM Cloud, once you go to the software tab here, you can generate something called as feature code, right? So though IBM Cloud is absolutely free to use for everybody, when you add a feature code which is only given by academic initiative, you even enhance the services that you get. So it is even better for you. This is not available to anybody but only academic institutions. So it's up to you whether you want to leverage this or not, right? Nobody can so that's what I wanted to talk about. So I'll take a pause here in case there are any further questions. Just you can unmute, you can ask, you can put it on chat. I basically joined today. I wanted to do a hands-on with you, but I guess we are not ready for that yet. So, I'll take a pause and maybe I'll close with this. Any questions, guys, that you have that, we can address? Any queries? Sir, for optimization, you can actually go and download the, ILOC Cplex, which is a globally recognized tool for, optimization. Again, you will have to go and you'll have to download it from here, right? I guess anybody who is doing research or who has done research plays with optimization problems, and plays how to use with mathematics and all those constraining problems. This is this ILOC Cplex provides you with a IDE, which with a very powerful optimization programming language, right? Cplex, right, which you can use, and there are a lot of these optimizer solvers available which are ready to use and can be integrated into the applications. Okay, any further questions, folks on the call? Anything else you would like to ask? I'll just like to leave it there because, in case you still look to, need access, or you can put those. I've already given these links on the mail. That's the reason you guys were sent in a mail also, right? Before even the first session, so that you can use it. I guess you are not in a process of actually using these mails and leveraging those. Yes, deep learning is also possible on this platform, Shruti. So in case your college hasn't given you a mail ID, institution one, you can get a temporary one for next 2 months from here. In case your college has given you a mail ID and the college is not registered so far, get the college added to the academic initiative portal. It's only for your own good, right? You can download so many software, you can download data sets, you can download all that here, right? So you can ask us to add the college through here. And once the college is added, you can definitely go and you can register and you can leverage that. Okay. Let's stop here. Is there any more questions? You can unmute and you can ask. Sandeep sir, are there any more questions?
Sir, I think there are no more questions. So I think we should wind up at this point itself.
Okay, sure, sir. No issues. So guys, thank you for your time today. We weren't able to do what we intended to, but then nevertheless, it was great talking to you. Thank you.
Thanks, Dr. Mani, for such an informative session, but I'm really sorry that our participant did not install software on the machines for the demo session. It's our bad luck that we're not able to get
no issues, sir. It all depends, right? So it's okay.
Session from your side. So I'm really sorry. I'm really apologize for that.
No issues, sir. Thank you. Thank you.
Thanks a lot, sir. Thanks a lot. The participants will again join at 2 o'clock for the last session of the STTP. Okay, and the session will be up to 3:15, and then we'll have a valedictory session for 15 minutes. And your test will be conducted at 4 o'clock. It will be at 4 to 4:30.
Sorry to interrupt, sir.
Okay. Sure.
Like how we can apply the data set for the using deep learning platform for my research area. So can I get his contact number or contact email ID so that I can communicate with him directly?
Dr. Mani, he has shared in his the PDF we have shared with you.
Yeah, same mail ID, right?
Yeah.
Thank you so much.
Yes, participants, any other query related to your test or for the last session? And the last session will be also a very good session that will be on the data science itself, and where Dr. Sukhjeet will be there. He will be discussing with us about the data science. The topic will be spatial data science, the importance of where. So I think that session will be also a very informative session. So I request all of you to attend that session also. And we'll see you at 2 o'clock. So thanks for joining this session.
Thank you, sir.